Welcome, everybody. My name is Pauline Gagnon. I'm a particle physicist, and I worked for Indiana University for 19 years as a research scientist based at CERN. And the last 3 years that I was at CERN, I was also working in communication for 3 years for the CERN communication group, writing blogs and discussing what we had discovered and all that, explaining what we had done for the general public. So that was became my specialty. Anyway, so today, what we're going to do is get a sense of what is particle physics about, because you're all graduate students, but in different fields. Some of them, you said you were in soft robotics, you're in applied physics. What are your fields of study? Gravitational waves, very nice. And okay, so biophysics. So all of you, you'll see I'll present the material in a very simple way, but to give you at least an idea of what we're doing. So I hope you got that. If not, at the end, there will still be time to do it. So I will present what is particle physics in a nutshell, then describe the tools of particle physics, and they're very simple. We have an accelerator to accelerate particles, and we have detectors to detect what comes out of it. So it's pretty simple. Finding the Z and the Higgs boson with the Atlas detector. So we will use real data coming from CERN, from the Atlas experiment, and we'll try to find Z bosons and Higgs boson. But before, I want to give you a little flavor of what is particle physics. So I hope I'm not blocking you. Okay. The aim of particle physics is to find the smallest building blocks of matter. And it's not so easy because they're so small. But if we were in Copenhagen at Legoland, Copenhagen, because that's where the Lego bricks were invented. And so they have a museum where everything is built out of Lego bricks. Of course, there it's very simple. If I want to see what are the smallest building blocks of matter, I take any of the exhibits when nobody is watching, I break it, and I see the fundamental particles coming out of it. And it's not so easy with real matter, but it's exactly the same thing. It's not so easy because they're so small. We all know that matter is made of atoms because we've been told so. And atoms are really small, 10 to the minus 10 meter. And inside the atom, you know, there is the nucleus and electrons that gravitate around that. Orbit around that. If I was the nucleus, how far would be, so my size, I'm the nucleus, how far away would be my electrons, do you think? 10 meters? 100 meters? Kilometer? 20 kilometers. So, in fact, matter is made of, it's vacuum. And the only things that prevent us from going through the floor right now, it's the electric repulsion from the electrons outside the atoms. But it's essentially just empty. Here's a real picture of an atom that I found on the web. An atom is 1,000,000 times smaller than a hair, so 10 to the minus 10 meters. But inside the nucleus, we also find other particles, and there are the protons and the neutrons. Inside protons, and they're already 10,000 times smaller than the nucleus. The nucleus is 10,000 times smaller than the atom. And quarks that you find inside protons and neutrons are smaller than 10 to the minus 19. We don't know their size because they haven't been measured yet. Maybe that's something that someone from your generation will manage. So if I ask you here, what are the real atoms that Democritus wanted to find, the smallest indivisible particle that exists, which ones would that be here on this picture? Quarks and electrons. Super. So those are the only real fundamental particles there. And with quarks and electrons, I can build all matter that we see around us. With you need two types of quarks, up quarks and down quarks. Up quarks have 2/3 of the charge of an electron, but positive, and down quarks have 1/3 of the charge of an electron, negative. And so with 2 up quarks and 1 down quark, you get 4/3 minus 1/3, it's +1. So you get a proton. How do I build a neutron with up quarks and down quarks? That's it. Up, down, down, and you get a neutral particle. So that's as much mathematics as we will do today. So that's just to know. And the standard model is this model that we have to describe everything that we know now about matter. And it's very simple. It has 2 basic principles. The first one is that all matter is made of fundamental particles, and there are only 12 of them, as you see. And plus, each of them has an antiparticle, so that makes for 24, if you want. So there are 6 leptons and 6 quarks. Leptons are like the electron, the muon, which is 200 times more massive, and the tau is 4,000 times the mass of the electron. All of them come with a neutrino, which is neutral. And so when you produce electrons, you always produce them in pair with a neutrino. And so I represent them here with small, soft characters that come from the particle zoo. A young woman, a seamstress in California, attended a lecture like this one night, and she thought it was really cute, all those particles. So she decided to sew them. And now you can buy for schools, you can buy a universe in a box with all the particles, and kids can play with them. All the particle physicists, their daughters and sons, grow up with them. So all matter is made of fundamental particles. Leptons, you cannot combine them. But the quarks, you can combine them, as we just saw with 3 quarks or 3 antiquarks. We can make particles or antiparticles. Up and down quarks are the 2 that I mentioned. Charm and strange, the 2nd generation. Strange is the 3rd one that was discovered. And because it had a strange lifetime, every particle that contained the strange quark had a long lifetime. And so, in fact, some particles had a long lifetime. They could not explain it. Later on, they saw that all of them contained that quark, and so they called it the strange quark. And once they were started, then the next one was called charm, and then they called that truth and beauty, but then someone said, whoa, 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 we have to calm down a bit. So truth kept the T and the B for top and bottom. The top quark is the heaviest of all the particles at 174 GeV. It's the most massive one. The weirdest thing is that it is as if I gave you a construction set like Lego bricks, but some particles are up to 4,000 times bigger than others. It's like you have Lego blocks and Duplo blocks, the bigger ones for the tiny kids, and so they don't match together. In fact, to form all the ordinary matter, all that we need is the 1st generation. The rest is totally useless. And we have no clue why it's there. But we see muons and other particles coming through cosmic rays, for example. We can produce them in laboratories. So they are possible, they exist, but they have no real use. We don't know why they are there. So there is still a lot to clarify here. And so all those particles interact with each other by exchanging other particles that we call bosons. Bosons are associated to forces, like the gluon is associated with the strong nuclear force, so that's what glues quarks together to form protons and neutrons, for example. And there is and it's a very short distance force, and the residual, there is some force that still leaks out of the protons and neutrons, and that's what binds protons and neutrons in a nucleus. Photons are associated with the electromagnetic force. W and Z boson with the weak interaction, which is also much more powerful than the gravitation, for example. Graviton, you're studying gravitational waves. We have found, it has been found now, gravitational waves, thanks to some very ingenious tricks to beat any type of vibrations and all that. But we haven't found any gravitons yet. although we suspect that they are there because every force comes with a particle, so probably the graviton is there, but we haven't found it. And the Higgs boson. The Higgs boson, which is associated with a new field of force called the Brout-Englert-Higgs field. And I'll explain in a minute how it works, so you'll have an idea. So how do particles interact with each by exchanging other particles? Imagine two skaters like this, and they're going on their own trajectory. And if one tosses a very heavy ball at the other one, both of them will recoil. Someone looking from far away will say, oh, there was a strange interaction at a distance between the two. No, no, no. It's just because they exchange a particle, and that's always the way it goes. This Higgs boson, you've probably heard about it, but it's not easy to understand what it does exactly. So in a simple words, I'm trying to explain it. So there were several theorists, starting with François Englert, Robert Brout, two Belgian guys who were working together, and Peter Higgs, who was working alone in Scotland. And these three were working in parallel without knowing that the other ones were there, but it was where physics was at the time, where the ideas were stuck. So what was happening was that in all the equations that come with the standard model, there are the two principles that I showed. Everything is made of particles, and particles interact by exchanging bosons. We could see that all the particles in the equations that come with the standard model were all massless. And we knew that those particles had a mass because we had measured them. So it was a bit of a problem. And so François Englert and Robert Brout thought of a mechanism. They said there ought to be a new field of force out there that gives mass to all the particles. And Peter Higgs had the same idea, and he wanted to publish his article. And he was turned down by the editor because the editor said, what a useless theory. You know, you don't predict anything new or interesting. Peter Higgs was a bit bummed out. He said, it comes with a new boson. Oh, I forgot to put it. So he resubmitted his paper to another journal, but this time he made sure to mention that it would come with a new boson. And that's why the boson is called the Higgs boson, because he's the first one to have named it. But Brout and Englert also knew that a boson would be there, but they didn't put it either on their paper. So Peter Higgs mentioned it, and as we will see, particles acquire mass by interacting with this field. A field in physics is simply something that modifies the properties of space around it. Like when you have a magnet, you can put iron filing, and you will see where the lines of forces are. How does a field, this Brout-Englert-Higgs field, generate the mass? Well, imagine empty space that was something like 10 to the minus 20 seconds after the Big Bang. There was no Brout-Englert-Higgs field. And then every particle could travel at the speed of light and had no mass. So a particle could go from point A to point B at the speed of light. Well, I'll do it a bit more slowly. So on a direct line. And this particle, all its energy was in the form of kinetic energy, and that particle has no mass. To travel at the speed of light, like photons, are massless. But something turned on the Higgs field, the Brout-Englert Higgs field. It's something like 10 to the minus 20 seconds after the Big Bang. Don't ask me more, I don't know. But that's what a theorist told me. And then the field was, the space-time was modified, and particles started interacting with the field. It's a bit as if earlier, an example, it was like an empty schoolyard, and I'm trying to run through the schoolyard. There's nobody there. I can run at my maximum speed. But during recess, when all the kids are playing, and if I'm trying to cross the schoolyard at full speed, I'll bump into various kids, and there may be some that I know, and I'll say hello and all that. So I'm starting to interacting with the space around me. And so this particle, when the field is there, starts to interacting with the medium around itself. And you see, it no longer goes at maximum speed, has less kinetic energy. But what happened to the remaining energy that it had to start with? Well, it cannot be lost. Conservation of energy. So this energy appeared as mass. Ta-da! So that's how the Higgs, the broad angular Higgs field acts. It's a non-dissipative field, so you don't lose energy like with a friction or something like that. And so the energy is conserved but transformed into mass. But I haven't said a word about the Higgs boson. I'm telling you that there is a field that is everywhere, that permeates everywhere in space. It is as if I have an aquarium here, and I'm telling you, this aquarium is full of water. And I ask you, can you see that? You don't see it. So if I tap on the window pane here, then you will start to see little wavelets. So that's exactly the same. You know that waves at the surface of the oceans, that you create them by giving energy. So the broad angular Higgs field is like the surface of the ocean. And the Higgs boson is like a wave on the surface of the fabric of the universe, the canvas of the universe. So waves are excitations of the ocean surface. So all we had to do was to excite the fabric of the universe to create Higgs boson. Once you have that figured out, it's not so bad. So Higgs bosons are excitations of the broad angular Higgs field, which is like the canvas of the universe. So all we had to do was to create Higgs boson by exciting it. And how did we do it? We did it with the Large Hadron Collider. So this is an accelerator that is near Geneva, right under the border, the French-Swiss border. And it's 100 meters underground, but 27 kilometers around. And there are 4 large experiments built at the LHC. Atlas, where I work, and CMS are the 2 largest ones. And we were multi-purpose experiments. We were looking at all sorts of things. We take everything that comes by. LHCb is mostly concentrating at figuring out what happened to antimatter, because every time we create matter in the lab, we create just as much antimatter. But when you look in the universe, there is only matter. There is no antimatter left. What happened? It's a mystery. And so that's what they want to see. And Alice is studying the conditions that prevailed just after the Big Bang. So 4 experiments. There are 13,000 researchers at CERN coming from 78 different countries. But in fact, there are countries having institutes like the Netherlands. There are many universities and institutes sending people at CERN. But altogether, there are 112 different nationalities that are represented. So it's quite a nice place to work. So the accelerator is underground with the 4 detectors built at the bottom in large caverns that were excavated. And each detector now is like Atlas is a detector that was built in the cavern, like you build a ship in a bottle. Now it cannot come out. CMS, they built it at the surface and then they lowered it. But they had better cranes, I guess. Ours is too heavy. And so what happened? We have the accelerator that accelerates protons at nearly the speed of light, and they bring them in collision in the middle of the 4 detectors that we have there. And the detectors are made of several layers, and they will detect all the fragments that come out of those collisions. So what will happen is that when 2 protons will collide, they will, the energy of the collision will be released and will materialize in the form of other particles. And so, in fact, it's not the protons themselves, but either the quarks inside the protons or gluons inside. There are lots of gluons as well. There is a sea of gluons inside the protons, and so that's what will collide. And it's like a mini firework, and we try to catch all the fragments and track them back and see what was produced initially. Here is how it works. So you have protons that are coming from a hydrogen bottle at the start, where we strip the electrons. So the protons they come in the first accelerator, second, and when they have enough energy, they enter the next stage. Now this one is 7 kilometers around. And finally, the LHC. And now you see the protons coming underground in the accelerator. And they're crossing the border several times. And then they will come, a bit excited, before action. And the protons will come and will be one from this direction, one from the other. In fact, it's millions of them in bundles. And they come together. They collide in the center of Atlas, and then something comes out of it. And we catch those fragments, and we try to tell what happened. The detector is made like an onion, several layers, and each layer is there to identify one property that these particles will have. At the center, the yellow part that you see here in the middle, that's what we call the trackers. Switching to French. The trackers. So there are 3 different layers of trackers just to see where they came from, and we make sure that all the fragments that we use, they come from the same collision point, at the very center. You'll have to check that later on as well. Then you have an electromagnetic calorimeter, and there particles lose some energy. And then the next one is the hadronic calorimeter. He's here outside. And finally, the first I think that's the first calorimeter, the second calorimeter, and then here's the muon system. And so the way it goes, particles coming through it will leave a track depending on their nature. Just like if there was a fresh snow here and I'm going through the forest, I can see tracks left by different animals, and they're all different. Someone with a bit of experience can tell the difference between a squirrel and a rabbit and a skier. So it's different tracks that people leave. And here it's also very, very different. For example, if you have an electron, this calorimeter here, the electromagnetic calorimeter, every particle that has reacts to electromagnetic force will leave energy there proportional to the inverse of the fourth of its mass. So an electron, which is very, very light, will deposit all its energy there. But a muon, which is 200 times heavier, will hardly lose any energy here. In the tracking system here, we only have the particles that have a charge, like an electron has a negative charge, so it leaves tracks here in the different layers of the tracker. Then it will deposit all its energy here in the first electromagnetic calorimeter. And by opposition, a photon will also leave all its energy there, but it leaves no tracks. So when it's dots here, it's because it's an invisible, a non-charged particle or invisible in the detector. A muon is the only particle that will be able to reach the last layer of the detector, which is called the muon detector for that name, for that reason, because it's the only one that, the only particles that can reach them. And any particle made of quarks, all the hadrons, so it's just a family name, hadron, is for all particles made of quarks, and those, they deposit their energy in that one. Okay, so what we will do today, we will look inside the detector, and we will be looking for leptons, electrons, or muons, and here are what they will be looking like. So it's a bit difficult here to see it, so I don't know if you see the red trace here, so it shows that it has a track, and then there is a deposition of energy here. We can enlarge the picture, and we see that it left a track in the tracker. So that's a clear sign of an electron. And there are two views in the detector. The detector is made in the shape of a tin can. So cylinders with end caps. Okay? And so we can look at it, this end view here, and the two particles, protons, the two protons come and collide here, and so there is no transverse energy or transverse momentum in that direction because they're only moving along the z-axis. So we can, the sum of all the energy or momentum that we find in that view should be 0. And so that's how we can find if there are particles that didn't leave any tracks in the detector, because there will be a deficit and there will be a lot of missing transverse energy. So that's an electron. In the end view or on the side view, you can see it here. And a mu1 will look like something that will also leave a signal in the outer layer. So mu1s are really easy to find. There are almost no fake tracks there and all that. Whereas you'll see the electrons are a bit more difficult to find. So what we will be looking for will be Z bosons. Z bosons, you can produce them, for example, one way to produce them, there are several ways, when two gluons inside the two protons will fuse together, we call that gluon fusion. Two gluons will fuse together and they will produce a Z boson, and the Z boson is very unstable and it will decay into two muons. And you can also produce Higgs bosons, but this time the Higgs boson will decay into two Z bosons, or that's one decay channel, and each Z boson can decay into two muons or two electrons, or two muons and two electrons. So you will be looking for events where we can find at least a pair E plus, E minus, or mu plus, mu minus for muons and electrons. And the decay, the Higgs particle, I told you that it was a fundamental particle. It's not made of something else. And so when it decays, it's not that, oops, it breaks apart and we find fragments of what was there. No, no, no. It's not something that you can break. You just take the equivalent in mass. Mass is energy. So you take this equivalent of mass and energy because of the momentum that it could have, and you transform it just like with money. When you put a piece of €2 to get change in a machine, it doesn't split your €2 in two, but it gives you the equivalent in energy. So that's the same thing here. So a Higgs boson can turn into two Z bosons and give us 4 muons. But it can also happen that we can produce two Z bosons independently, and each of them will decay into 2 muons. So when we find 4 muons in the detectors, and they would look like this, with tracks, very, very energetic tracks extending to the muon system, we can never tell if this was coming from a Higgs boson going into two Z boson, or if we started simply with two Z bosons that were produced independently. The only way we can tell the difference is with statistics. And so what we need to calculate is the invariant mass, a mass that doesn't depend on the rest frame. And if you take the 4 vectors, you get E squared minus P squared is M. When you put the units of C equals to 1. And so you can extract the mass, the invariant mass of the initial particle that was there. If you find 2 muons, or 2 electrons, so you take the energy of the first, the electron, plus the energy of the positron. You don't have to use this equation. The program will calculate it for you. So otherwise, you would be doing that like maniac for. So we have a little algorithm that calculates it, but that's where it comes from. E squared minus P squared, and that's the invariant mass that we will calculate today. Okay, so how do we distinguish an event containing a Higgs boson from all other events? Theorists can tell us the distribution that two Z bosons will have based on statistics and Monte Carlo simulations, and they can tell us that it would look like a distribution like this, okay? Where we have here the combined mass of the 4 muons, and here we have the number of events that we found in the data. And so if the Higgs boson had a mass of 150 GeV, for example, then you would see an extra number, a peak, appearing here, all piling up at 150 GeV because they all come from the same initial value. Instead of having two Z boson, each of them will come with some momentum. So when they combine the four muons, you will have a random distribution, or not random, but this, like that. Do you get that? Is that clear? Yeah, okay. And that's what we did. So we started collecting data in 2010, and each dot here is one event with four muons, or four electrons, and we accumulate them, and so the red curve here now shows what we would have from the background, ZZ events. And you see, starting in 2012, we start seeing a peak appearing here, all an excess of event showing up here, and that showed us that the Higgs boson had a mass of 125 GeV, and we had a nice party after that. That was really nice to find. So that's how we found it. We'll be doing the same thing today. I can show it again, except that if we, I don't know if we will have enough data with 8 or 9 teams today to really see the peak appearing, but we will see it certainly in the Z peak. But for the Higgs boson, I'm not sure if we will see it. But we can, you'll get an idea of what's happening. So you can see it here accumulating. So in December, we announced it on the 1st of July, 2012. And so we didn't have many events, but already we could tell that there was an excess. Okay, so we'll go now. I think you have already set with the thing. I want to tell you, I brought some copies of my book. It's a book on particle physics for everyone. So it's you saw the level of mathematics that I use, and so if you want to learn more, everything about the Higgs boson, CERN, and all that. But also there is a chapter on diversity and on Mileva-Maric, Einstein. Tomorrow night I will be giving a talk when everybody will be absolutely stuffed and drunk. I'll be giving a talk on Mileva-Maric Einstein, the first wife of Albert Einstein. She was his collaborator all for 20 years, but she's absolutely unknown today. So you have this program, and I would ask you to go in that place here. You can see, I think, the word group or something like that, and select the 4,000 events. So in that, there are 4,000 events group in the, I don't know how many groups there are, 80 groups of 50 events. So each of you here will be using a packet of 50 events that you will analyze, and at the end we will combine our statistics. And I would ask you to work in pairs, so it's more fun and it's more efficient. So let you distribute yourself. So you will select here 4,000 events, and then I want you to select the PT cut at about 10 GeV. So here, to the left of the box with the 1,000 events, you have a PT, and put that to about 10 GeV. It means that it will remove from the display all the low momentum tracks that are not interesting. Because to create heavy particles like Z or H boson, it's only when you have a head-on collision. When they just graze each other, you know, it's junk that produced Nobel Prizes but 10, 20 years ago. Today it's junk. So, and we will be looking for events with lepton pairs. So you will always want a pair of E plus, E minus, or mu plus, mu minus for the Z bosons. And for the Higgs boson, then you need 2 of those pairs. So any event with 4 nice tracks, and you enter everything. So let me, then at the end we will look for Z pairs to find Higgs boson. So we will do that all at the same time. So I don't know how you want to form your teams here. You're 5 on this row. So let's say that you take the first set of events. you'll take the second set with whomever you work, third set, fourth, fifth. So maybe you work together. Number 6, number 7, 8, 9, 10. You can either work alone or with other people. It might be nicer. Okay, so then we will have 500 events analyzed, and then maybe we have a chance to find something. Let me, and then at the end we will look for, at the end we will save at least 20 minutes, half an hour to combine our data. I will have a spreadsheet here on the computer, and then we can, I'll just switch gear here on this here. No. Okay, so I have this here, but you're all familiar with playing with that kind of thing. So it's not projecting here. I must not be at the right place. No, yeah, yeah, Alt Tab. No, I'll let you do it. Okay. Okay. Yeah, I think that's good. That's good. Yeah. It's not on screen. Okay. It'd be good to have it on screen. I think it's coming now. Perfect. Thank you. So, as you can see here, you can select. So I'm on group here. So let's look at the first event. So we're spoiling the show for your first event. So here you see I have clearly a mu1. You see on the, so if we are on the first set of events, if you look here, I'm on the, oh no, it's not there. Here I'm event 0, we should be able to read it somewhere. It will come. Okay, so if I click on one track, like this one, then it turns purple, magenta, okay? And then for this one, I see that it's a mu1, so I say insert it as a mu1. I already selected it, okay. And then you see that it's shown as a plus, so it's an anti-mu1. And if I select the other track here, that track is negative, so that's a mu1. And I would also insert it, but I did it while I was doing the setup, so it's already in. Okay. And now I can look at the combined mass, and I have a combined mass of 94 GeV. And we'll see, we'll find different values, and at the end you'll see why we'll have different peaks in that distribution. And then I can go to the next event here, next event. And again, it looks like two mu1s. I'll go at here, it's a bit more tricky because it's electron. I can increase, I can zoom a bit. So there seem to be nice tracks. Here in the dotted red line here, it's the missing energy. So they were neutrinos or other things that are not visible, maybe dark matter or something like that, that is not visible in the detector, and so it leaves missing energy. The total momentum and energy in that frame is not balanced. And so you can see here, we can select this one track as 13 GeV, and it's positive, and the three of them are positive. We're not going to make a nice pair out of that. And you see, because it's written. Sorry, I'm looking there, but okay. So here is the charge. And so you see when I click on a track, it lights up here. If I go back to the first event, previous event, so when I click on a track or here, if you selected tracks that you don't want to have, you can remove them here by delete track, and you have all the possibilities to delete all of them here in that table. And in that table, you can, if you go further here, you see also if it was an electron or a muon that you selected. you see the charge that you have and the combined mass for the two of them. And so here I only had 2 muons, so I can only form one particle. If there had been 4, I would have another mass, invariant mass here. Getting the gist, yeah? Okay, so we'll go to an event with electrons. That's junk or something. See, for example, here there is a large deposit of energy here. In the green is the electromagnetic calorimeter, but there is no track associated with that. What is this? Photon, that's it. So you have photons here, 2 photons back to back. Probably that the 2 photons would form a Z as well. Z going to 2 photons is also possible. Okay, but we're only looking for leptons, so I'm going to go to another view. Again, here it's clear that those are muons. We'll go to this one here. There are possibilities that these are electrons here, like this one. I will insert it as an electron. And that one, so that was a negative track. This one is positive. Allez up. We have some luck. And it forms a mass of 21, very different from the other ones. But you'll see at the end why we have different masses like this combining when we do the combination. And I will put up here a spreadsheet. And when you have, note your event number and the mass of the 2 leptons or the mass of the 4 leptons that you have. And I will put them in my spreadsheet and we'll try to do distribution with that, okay? Okay. Allez hop, c'est parti mon kiki. Yes. Sorry. Why are there? See, this event has 2 electrons, that's clear. And that's the same, that's the opposite view. And here we can see that these tracks here, this one, for example, this one is a muon. So this event has 2 electrons and 2 muons. So that's a good candidate to find a Higgs boson here. Does it answer your question? There will be extra tracks as well because there are also underlying events where there are millions of protons coming at the same time. So there are, on average, 37 collisions on each event that we record. So we must make sure that the tracks that we take, they come from the same point here at the center, that they all merge together from the same point. Okay? So you try that. Good luck. And you all have the consolation prize for, at the end of the day, we all get a beer for finding whatever we find. So. So we're having trouble. They gave me a spreadsheet on the web, and it just doesn't want to work. So I'll have to use the results of another group. So what they did here, by looking at different, you see, electrons are in blue, and the muons are black. And you can see that there is a peak, and there are various values that enter here. This here is something that was artificially added as if there was a Z prime. This is one particle that we are hypothetically looking for, a Z prime. So a type of particle that would decay also into E plus or mu, E plus E minus or mu plus mu minus. And so they put it at a mass of about 1,000. And so some of those fake events are placed here, and you see them here. And for the data that you gave me, but I could not quite compile, we should be getting something like this. Lots of events around. The real value of the Z boson is 91.14, I believe. And so 91 GeV. So we see that they peak here. And there are others because here there is another peak, which is the epsilon peak, which is made of BB quarks. So two BB bar quark, the upsilon, and it also decays into E plus E minus, or mu plus mu minus, but its mass is around 10 GeV. And then there is another one, which is the J psi, which is made of C bar, so C quark and anti-quark C, and you get them here. For the events where you have a Higgs boson, the Higgs boson, as we found out, had a mass of 125 GeV. So if you want to produce two particles that are at 91 GeV, starting with 125, it's like you want to buy two objects that cost 91 euro, but you have only 125 euro. So what do you do if you're short of money and you want to buy two shirts or whatever that cost 91 euro each? You go and you ask a friend to lend you some money just for a short time. And that's exactly what the Higgs boson does. It will create, in fact, virtual Z's. They're not unshelled, that they're right on their mass, but they will be slightly below, such that you can produce 2Z. So one will be unshelled, but the other one will have a mass that is anything below the central mass here. So we see lots of entries that come anywhere here. The Z peak, let me check if I have it here on this. So this was the combination for the, my Indian friend in Mumbai. She did that, and that's what they had. Here is the plot for All Institute. Diphoton invariant mass, so diphoton we didn't do. Lepton invariant mass, 4 lepton, 4 muons. Okay, so here is what they found for the Higgs boson, and the mass is a bit brighter. How bright it is depends on also how long it will live. So you see here that there is some sort of a peak around 125, but it's quite bright, and it means that it has. It will also have a short lifetime because of that. The lifetime of a Higgs boson is 10 to minus 25 seconds. Doesn't last very long. So we'll never do anything useful with the Higgs boson. It's useful because now we understand better how things are going. So humanity can go to bed tonight being a little less stupid. We know a little bit more about how nature works, but we'll never do anything useful with the Higgs boson. What is useful in particle physics is everything that we develop, the techniques that we develop are used in the medical imaging, for example, or with hadron therapy against cancer with the Bragg peak, where you can use beams of particles made of hadrons like protons or carbons, and you get a much better effect than with conventional therapies, X-rays. So you see we have a nice peak here, and so the 4 muons, there were not so many events, but the muons, of course, are the ones that were really easier to find because they're clear-cut. A muon, they're really rarely a fake muon, whereas all the other charged particles like pions, protons, they will deposit a bit of energy in the electromagnetic calorimeter, but also some in the hadronic calorimeter, the red layer outside the green layer. So that's roughly what we would have seen, but of course that's not the way we work to find the Higgs boson. We had algorithms to do it, and it's just afterwards that we look at the events to see if they seem to look like reasonable events and all that. But it gives you an idea of how these things work. So sorry that we couldn't get our own plot here, but thanks to my friend Sudeshna Banerjee for sending me her results. That's at least I can show you. But I don't know, this spreadsheet, and normally I think they have 3 hours to do the class, so then you have a bit more time to enter your data and all that. But I hope you had some fun, and if you have questions also, I'm happy to answer them. Did you learn something? Yes. Yes. I would have to go back to my slides. Bon, now it's on the other computer. Let me. The reason is that the muon deposits the energy deposited in the electromagnetic calorimeter is proportional, inversely proportional to the fourth power of the mass. The muon is 200 times heavier than the electron, so it will deposit 200 times to the fourth less energy in the electron calorimeter. When it gets to the hadron calorimeter, it's only particles made of quarks, hadrons, that will deposit a lot of energy there. So the muon is a lepton. It's not made of quarks. So it loses very little energy in the electromagnetic calorimeter, almost nothing in the other one because it's interaction with the nucleus in the detector, and then it can leave a track. It's just a tracker outside for the in the muon system. But the only particles that reach that are muons. Tau particle is also quite unstable, and it will usually decay into an electron and a neutrino, or and two neutrinos, electron neutrino and tau neutrinos, or a muon with a muon neutrino and the tau neutrino that comes with the tau. And so those you find them. And so that's why sometimes you find electrons, but the Z can also go into two taus, but then it's much more difficult to reconstruct it. Yeah. Did you learn something about a bit about, get an idea? That's good, that's good. Do you think you deserve your free drink? Good. Any other question? Yeah? Live longer? I once knew. It's probably a simple answer. I can't remember. Sorry. Muons can also decay into electrons, but it doesn't happen so often. But they do decay. Then it will, just like the tau, it will give two neutrinos, so they will have a lot of energy, and the electron as well. So the energy is split between the three. Yeah, but the muons are relatively stable. But all the other pions are stable. Pion is made of an up quark and a down quark. So I showed you how we make protons and neutrons. So they're made of 3 quarks or 3 antiquarks, for an antiproton, for example. And there are so those we call them baryons when they're 3. And there are some mesons. Those come with a quark and an anti-quark, like up and down quark. Then you have a charged pion, for example. Or kaon comes with up or down and an S quark. And then, so up and down quark, and you can put also an up and an anti-up quark, but they don't have the same color, so they don't annihilate each other. There are 3 colors. Quarks come in 3 colors. That's why it's called quantum chromodynamic, because of the color. So there are 3 types of. So matter is much more simple than Lego blocks. In Lego world, there are 3,700 different particles, and as I showed you, there are 12 basic particles for matter and 6 or 7 for bosons. So it's plus the antiparticles. So it's about 20-some. 23, I think. So it's much simpler than Lego world. You can also build the Atlas detector with Lego blocks, and there are sets for that. Some maniacs, some physicists working on Atlas who were maniacs for Lego blocks decided to submit a project, and it was done. Anyway, so are there some Lego enthusiasts here? No. Yeah, they are sort of modern, and they always make new parts for specific projects and all that. And they also have many colors. We have 3. Yeah. So we don't get the mass directly from the detector. We get the momentum, and the momentum we get from the curvature. So we have very large magnets. So a charged track will curve, and that's how we get if it's positive or negative, in which direction it curves. And so from the curvature, we can infer the momentum. But most of the tracks that you were looking at, like the muons, no, they were really stiff. We call them stiff tracks because the muon is so much lighter. It's 200 MeV, I think, and it's so much lighter than the Z boson, which is at 91 GeV. So it's a very big difference. So the muons come out with lots of energy, so they hardly bend in the detector. And so we have also those magnets, because tracks that have very low momentum will just curl up in the tracker and lose their energy there, and they don't mask the rest of what is interesting. But telling the difference between the different tracks, as you saw, is relatively easy. So as I said, it's a bit like with tracks in snow. It's all the difference between a muon and an electron and the photons are quite striking. With pions and kaons and all that, then it gets a bit more complex, but it's feasible. It's feasible. Yeah. We cannot make sure of that. It's what we have. It's like bundles of protons. In each of them, I can't remember how many millions or billions of protons there are in each of them, and they cross every of nanoseconds. There are 5,700 bundles around 27 kilometers, and they cross each other. On average, we have 37 collisions happening at the same time. So the way we tell them apart is by looking which tracks come from exactly the same point, close to the Z axis. And that's we only select tracks that are coming from the same point. So I don't know if some of you checked that sometime, that the 2 tracks were really pointing from the same origin. But no, we didn't have that much time to do it. But that's how we tell the difference. But it is as if we're taking picture. I don't know if you're a bit too young for that, but I used to have a camera. It was a very nice Pentax, with and I am from Canada, and I wanted to. I went outside. It was minus 40 degrees that day, Celsius, or Fahrenheit. It's the same scale. Minus 40, and I hadn't seen that often. So I got really well dressed, and I went outside. And I wanted to take pictures, and my camera froze, and because it was all metal and metallic, and I couldn't move it anymore. And all the photos were superimposed, and so that's what sometimes it made for interesting effect, but other time it was just a waste of negative. But that's also what we get with in the detectors. All the events are piled up, and it's only by looking from the vertex. So our first tracker, in fact, is called the vertex detector. So it's very, very close to the interaction point, and we look at if the tracks really emerge from the same point. And yeah, it's the detector that is the closest to the interaction point. And it's made, it's made of pixels, so it's like the technology that is used for digital cameras. And the next layer is with silicon detectors, and the third one was made of gas. It was called the transition radiation tracker. That's the detector that I worked on to build, and that was made of. We had straws that were about a meter 40 centimeter long, 140 centimeter long, and it was filled with gas. And when a particle with a charge crosses the gas inside, it will ionize the gas. Then we had a small hair type of wire inside, very fine wire, and then with the potential difference between the straw and the wire. And then when the gas is ionized, all the electrons will drift to the wire, and then we get a blip, and we know that it has been hit. So, and then just like when we were kids, we connect the dots. We had 37 layers, and we connect the dots, and we can tell where the particle went through. So we have 37 layers of that detector, so it was fairly large. And then the small one was silicon, so that's more precise, but on a short distance. And then the most precise was the vertex detector, very close to the detector, the interaction point. The detector is huge. It's 7,000 ton. It's like the Eiffel Tower. The Eiffel Tower is made of rusted steel, whereas the Atlas detector is all made of handmade, very precise, tiny parts. So, like my friend Monica Dunford used to say, it's like a Swiss watch on steroids. It's steroids. It's just huge. It's dimensional. And it has 4,000 kilometers of cable inside the detector and 4,000 kilometers of tubing with all sort of coolant or gas, like in our detector of ionization and things like that. It's quite a complex thing. The most amazing thing is that we turned it on and it worked. It worked. It was amazing. That was but of course we had tested, and retested and endlessly. But when it was time and the first collision happened, and it was quite amazing. Yeah, so that was fun working there. Yeah. If you have a chance to go and visit at CERN, don't miss it. Go in the winter between Christmas time and April, because then it's the annual maintenance, and you can go underground and visit the detectors. And every 5 years or so, they do open days. It's wonderful. You can visit everything, and it's completely crazy. There are tons of things that you can see, so it's really worth it. I don't know when the next one is foreseen, but it's advertised. I was there last time, and there were people coming from all over the world to have a chance to see it. It was quite amazing. Okay, 6 o'clock. Thank you for coming. I hope you had fun. I did.